I can see it fine through my picture window. I don't need to be out again.
Okay, well, I think we should get started and maybe some other people will join us, but it doesn't really matter because we're all here and that's what counts. So there are a few things that are coming up that will be exciting in the next month or so. First of all, the moon is at first quarter today, so and it's going to be full on March 3rd, which means it will be getting bigger as we go from first quarter around to full moon. And there's some excitement. The next on March 3rd, we have what's called the worm moon. I guess because people think the worms are coming out because they think spring is coming. Maybe not here. But there will be on that day a total lunar eclipse on March 3rd. It's principally visible from the western portion of North America, but if you want to get up early in the morning, you can see it, and I'll review that in a moment in the next slide. The other thing that happens in March is on the 20th, that is the vernal equinox, when the sun's path across the sky crosses the celestial equator into the northern hemisphere, and that is the first day of astronomical spring. And the other thing that happens, which I hadn't fully appreciated when it happened, is actually on Sunday, March 8th, which is not far in the future, we actually go on to daylight savings time and lose that hour of sleep. I guess it's good. It will be bright in the evenings and in the late afternoon, but it will mean that it's dark in the morning again for a while. So let's get back to this total lunar eclipse. A lunar eclipse occurs when the moon moves through the Earth's shadow, and that happens at full moon. And for us in Ithaca, the totality will be visible, but it will be visible only when the sun is very close, when the moon is very close to the horizon, setting in the west. So here's the timing. It's always good to you can review these things at timeanddate.com. They have a really good page which talks about the timing, and you can put in any place on the earth, and they also have lots of nice animations and things like that. The total eclipse begins at about 6 a.m. and sunrise is half an hour later. So it will really be, you'll be able to see the totality part. When the moon turns typically red, because of scattering in the Earth's atmosphere, allows some light to be reflected off the moon. But it will be hard to see in the sense that it will be uh, close. It will be occurring about the same time. It will be in the west, but it will be occurring about the same time that the sun is lighting up in the east. So anyway, of course, the other thing is it has to be clear. I can't promise that. And there are some other things that are interesting. Mercury, most of the month of March, will be in the sun's glare, but it will be slightly visible above the horizon in the last days of this month. Um, Venus will be bright, but it will set in the west in the early evening. Mars is in the sun's glare and is not visible. It's in the direction of the sun. Jupiter is in the southeast at sunset, visible most of the night, and Saturn sets soon after sunset, so it's hard to see. Again, you can all go to timeanddate.com and ask them what planets are up, and it will tell you. There's an interesting event that's going to take place on February 28th, later this week, and that is a time when six of the planets are actually above the horizon at the same time, spread out. So here's a depiction of what will be visible. Uh, Six of the planets are up. Of course, Uranus and Neptune, two of them are not visible to the naked eye. But if you look towards um, the in the night sky, towards the west in the early evening. Venus, which is very bright, will be just above the horizon. Mercury slightly above and to the right of it, and then Saturn above that, and then Jupiter is over here. Alan, you have a question?
Yeah. Um, since all the planet orbits are pretty close to the ecliptic, I was wondering why does one talk about things like all the planets in a line as
It,
a,
it's
a
it's
significant event?
well, just that they're all in roughly the same part of the sky at the same time.
So it's the
And
same part of the sky part, really,
and
not
and but it's also true that they're following a path, which is the path of the ecliptic plane or the constellation of the zodiac. So they're always following a band across the sky. In fact, they're not exactly in the same direction. Jupiter is off by some 80 or 90 degrees, but nonetheless, they're kind of in a band. But this idea of planetary alignment or planetary parade, I agree with you. It doesn't mean a perfect line. And they are in a band, as you've said, which I'm going to show in just a few slides. They always follow the same path which the sun and the moon follow in the course of a day and also through the year, because all of the orbits are in the same plane. But it's not that usual that you have a whole bunch of them visible at the same time. And astronomers, like everybody else, likes to make it sound like it's a special time and you should all go outside and look up. Okay, so let's talk about the planets in the solar system. And you know that there are 8 planets, um, two of which are interior to the Earth, and the others, which are exterior or orbit further out than the Earth does. Um, Mercury, Venus, Mars, Jupiter, and Saturn are visible to the naked eye. And what distinguishes the planets from the stars is as long as it's not too totally um, uh, cloudy, you will see that the planets don't twinkle the way the stars do. They also wander among the stars during the course of a year. There are differences in the apparent motions between the two inferior planets and what we call the superior planets. And that's due to the fact that these planets are never seen very far away from the sun. So Venus and Mercury, because they have little orbits that go around, they're always visible before sunrise or after sunset, but they are not visible at midnight ever. And the other planets, uh, Uranus and Neptune, of course, are not visible to the naked eye, but they all travel or in lengthy orbits along the same plane, but they sometimes are visible at midnight. Another thing to point out, and this is directly relevant to what we're going to talk about tonight, is Mercury and Venus are close to the sun. And so they are heated up. They would be hotter naturally because they receive more sunlight. As you go further and further away from the sun, the planets receive less sunlight, and therefore they are colder. But and a related fact due to that is that the inferior planets, as we call them, the ones and plus Earth and Mars, the ones that are relatively close to the sun, are rocky, um, and they're relatively small, whereas the outer planets are gaseous and very large. And so we're going to talk about the planets in the solar system and how they're different one from another. And then we're going to step outside and take a look at planets that we know around other stars. So let's remember that we have the sun and we have the earth and the moon. And each one feels the gravitational pull of the other two. The Earth orbits the sun. The moon orbits the Earth as the Earth is traveling around the sun. And the motions that we see are governed by gravity. And the laws of gravity that cause the moon to revolve around the Earth and the Earth to revolve around the sun also applies to other planets and other moons, the moons of other planets. So here it's just a little animation that shows the orbits of the inner solar system. So we have the sun, Mercury, Venus, the Earth, and moon system, and Mars. And let's think about a few things about this little animation. First of all, the planets we know revolve around the sun following elliptical orbits. And so if you look at Mercury's orbit here, of course, this is grossly undersized and the ellipticity is actually exaggerated somewhat. You can see that Mercury's orbit is not circular. Instead, what Kepler figured out was that the planets revolve around the sun following elliptical or elongated orbits. And if you remember from geometry, and we'll take a look at this in a minute, an ellipse is elongated. A circle is a special kind of ellipse where the distance from the center is all the same. If we have what we talk about when we talk about an ellipse are the two foci. And in the case of the orbits of the planets, the sun lies at one focus of the ellipse. The other focus, which would be where my cursor is pointed, is empty. And if you see here, you see that Mercury is sometimes a little closer to the sun and sometimes it's further away. You see the other orbits are also closer to, not as elliptical as Mercury, but they're not perfectly circular either. And another thing to notice is the planets all orbit the sun in the same direction. That's important. Okay, so here's our little diagram of what an ellipse is. I'm sure you all remember someday you took geometry one time in the past. And so this is how we define an ellipse. And again, the Earth's orbit is ever so slightly elliptical. What's curious is that when the sun is closest to the Earth, what we call perihelion, the difference is about 5 million kilometers or 3 million miles, but the Earth is closest to the sun in July, and it's furthest from the sun in January. So I hope that tells you that the ellipticity of the orbit does not cause seasons here on the Earth. Okay? One might think that would happen, and when we talk about some of the weird exoplanets, which have very elongated orbits, we would expect that the ellipticity of the orbit would cause a big change in the amount of radiation that the planet receives when it's close from when it's further away. But for the Earth, it doesn't make much difference. So again, back to, yeah, Alan.
I'm sorry to nitpick, but I was really pretty sure that perihelion was in January, not July.
No, it's the other way around.
Hmm. I mean, I always thought there was the big lesson. It was all counterintuitive for us in the Northern Hemisphere. Summer is our warmest time, and yet we are furthest and
Yeah,
going slowest.
I take it back. You're right. I got it confused. We are closest in the wintertime in the Northern Hemisphere, and we are furthest in the summer. So that is why we don't have seasons. You're right. My brain was dysfunctioning. And that we'll see why we actually have seasons in a moment, because it's due to the tilt not the difference. We'll also talk about Mercury, which has a different tilt from us, and which also has an orbit which is elongated enough to make a difference. Okay, so planets revolve around the sun following elliptical orbits. They travel in the same direction, and the orbits are all slightly, but not very elliptical. The only one that really has a significant ellipticity is Mercury. Again, we just mentioned this, Alan brought it up before. The orbits are roughly in the same plane, like a disk with the sun at the center, and then there's an imaginary disk in which the planets orbit around. And the orbits all lie almost in the same plane. In fact, the only one that really tilts out of the plane is Pluto, and that's one of the reasons, or yet another reason that we think that we don't classify Pluto as a planet anymore, because it really isn't distinctive. It's not big enough. It crosses inside the orbit of Neptune, and doesn't exert its own gravitational force enough to get it and be massive enough to classify it as a planet. The other thing, and this diagram is intended to show it, is that the planets orbit in the same plane and they all go in the same direction. They also, some of them have different tilts, but almost all of the tilts are relatively small, and they are also tilted in a particular direction so that they're all more or less like this, as opposed to being like this, with an exception, with two exceptions. Now it's the tilt that causes the seasons. Okay, so the tilt is the Earth rotates on its axis at the same time that it's revolving around the sun. And the axis of tilt is not perpendicular to the plane of the orbit, instead it's tilted. And what that means is that in June, the northern hemisphere is tilted towards the sun, and in December, the southern hemisphere is tilted towards the sun. And that has two consequences. The first is that the path of the sun across the sky at a particular location is higher, and therefore the length of time the sun is above the horizon is longer in summertime than in wintertime. So you get more sunlight, which means you get more heating. And the other thing is that the sun's rays are more concentrated on an area in the summertime. They're more direct. And in the wintertime, they're at an angle, so the rays are spread out over a larger area. And so you get less concentration of the heating. And that's what causes the seasons. And I bring this up because if we actually look at other planets, they don't have the same tilt. And if you were on one of the planets, you would experience different kinds of seasons. So notice here are how tilted are the planets. You see that Earth, Mars, Saturn, and Neptune are roughly tilted by about the same amount. On the other hand, Mercury and Jupiter are almost not tilted at all. And Uranus is weird because it's like tipped on its side. And Venus is also peculiar because although its rotational axis is almost perpendicular, like Mercury, it's actually upside down. So that's a question that when we're talking about planets and what it would be like to be on one of these planets, You have to understand that depending on the tilt, you'll get differences in the seasons. In Mercury, you won't have seasons due to the tilt. There won't be seasons. And if we think about the development of life here on Earth, the fact that there are seasons is important. You don't grow the same crops at all latitudes because different latitudes have more extreme seasons. So we just throw that out there as something to keep in mind. Okay, so here are our planets, and we have rocky planets on the top, rocky inner planets, and we have gaseous and large planets on the bottom. What you don't see in this is that these are all much smaller. The rocky planets are all much smaller, relatively warmer, and closer in than the gaseous planets, which are on the outside. So let's review a little bit about them. Okay, the inner planets are rocky, which essentially means that they're dense enough that we think they can't be made up of just hydrogen and helium. They have to contain things like carbon and aluminum and iron and silicates and stuff like that. The Earth is the largest of the inner planets, and curiously, some of the moons of the outer planets, like the moon Titan, which is a moon of Saturn, it's almost the same size as Mercury. It's a little bigger than Mercury. It's smaller than Mars and the Earth. Venus and Mercury, of course, are very hot. They have temperatures that we would not find comfortable. Mars is quite a bit colder than the Earth. So the average temperature on Mars is about minus 80 degrees Fahrenheit, whereas on the Earth it's more like 60 degrees. The Earth, just the comparison of Earth and Mars is that Earth is larger, it's denser, and has a stronger gravitational pull. Mars is smaller, less dense, and colder. Mars has a very thin, mostly carbon dioxide based atmosphere, whereas the Earth's atmosphere has nitrogen and oxygen. Mars has vast amounts of water ice, primarily at its polar caps. And then those are the caps have the water ice plus they're mixed with dust. And then they have a seasonal layer of carbon dioxide ice, which gets deposited. The giant planets, in contrast, are giant. So notice here the size of the giant planets relative to Earth. This is Jupiter, Saturn, Uranus, and Neptune. They're all very large and cold. Jupiter and Saturn are composed principally of hydrogen and helium. So they're called the gas giants. Whereas Uranus and Neptune are called ice giants because they also appear to contain heavier elements like water, methane, and ammonia, all of which at the temperatures of those planets are solid. And so just keep in mind that these planets contain hydrogen and helium and maybe some water, methane, and ammonia, but they are generally gaseous and they're really, really cold. Okay, so back to our picture. So if we were to step outside the solar system and could look back, we would see these tiny inner planets, and we would see these giant outer planets, which are cold. Now, what we're really interested in, although we're going to talk about weird planets today, of course, one of the fundamental things that we're interested in is whether or not there are planets that could host life. And when we talk about that, we talk about what we call the habitable zone around a star. And the habitable zone is a region outside of the star where if there's a planet in orbit at that distance from that star, the temperature of the planet will be just right, not too hot, not too cold, so that liquid water could exist. Okay? So the habitable zone depends on what kind of a star you have. We have a star, the sun, which is kind of a middle-sized star, middle temperature star. Um, and the Earth is just at the right distance from the sun so that liquid water, as we know, exists. Mars is a little further out where it gets a little bit too cold, although there may have been liquid water in the past. Venus and Mercury are too close in, so the temperature is too high for liquid water to exist. And when you get to the outer planets, likewise, they're too cold. Although we believe that there may be some liquid water underneath the crust of some of the outer moons which are covered in ice. Okay, back again a little bit to our orbits, which we have to keep in mind. Notice that the orbital period, the time it takes to go around the planet, is short. Mercury goes around a few times while the Earth is cruising around. Venus also has a shorter orbital period. And if you watch this really, really closely, it's hard to see, but Mercury travels a little bit faster when it's closer to the sun than it does when it's further away. And that's because Kepler came up with three laws for planetary motion. The first one was that the orbits are elliptical, not circular. The second is that the area swept out in a given time. So if this is 1 month of the year of this planet, and this is 1 month, they sweep out an equal area between the orbit and the distance to the star and back out. This area is equal to this area. This time is equal to this time. And in order to travel this path length, which is longer than this one, in the same amount of time, say 1 month, the planet has to move faster in this part of the orbit and slower in this part of the orbit. So that the star moves faster over here and slower over here. And what Kepler was able to show was that if you look at all the planets, that's for an individual planet, the second law. And for all of the planets, the distance from the sun tells you how fast the planet has to move in its orbit and what its orbital period is. It governs the speed of the motion of the planet in orbit. And that works as the orbital period squared is proportional to the semi-major axis cubed. And using that law, you can figure out how far away the planet is and in accordance to its period. And my real point in bringing this up is just that we understand that the laws of gravity dictate Kepler's laws, and that those laws apply in other systems. Planets will travel faster. This is actually a depiction of Mercury's orbit. Mercury's orbit is quite elongated, and in fact, it will travel faster over here and slower over here, which means it spends more of its time over here and less of its time over here. We're going to talk about some planets that around other stars which have extremely elongated orbits, which means they spend most of their time very far away from the star, but then they may come very close to the star for a short period of time. Those planets would have a hard time developing life just because the temperature on the planet could change dramatically depending upon where it was in its orbit. Okay, so let's just talk about some weird exoplanets. I'm going to talk about planets that don't have stars. They're out there, but they're not orbiting a star. Those are pretty weird and we don't understand them very well. We're going to talk about planets with very strange orbits. We're going to talk about a category of planets called hot Jupiters. They're like Jupiter in terms of their size and mass, but they're much further, much closer to their parent star, so they're really, really hot. We're going to talk about Kryptonian planets, which are planets which seem to be actually changing their nature from being a gas giant like Jupiter to becoming a hot Jupiter, and maybe even becoming something else. We'll talk about warmer hot Neptunes, which are planets that are similar to Neptune, which means that they have masses 10 to 20 times the Earth mass, but which orbit much closer to the star. And we're going to talk about super Earths, which are rocky planets like the Earth, but they are 2 to 10 times more massive. And then we'll also talk at the end around the Earth-like planets, planets that we say are actually somewhat like the Earth. But first, I have to make a disclaimer, and that is, and I'll talk about this some other time, how we find exoplanets. We have several different methods that by which we can find exoplanets. There's really only one or two extrasolar planets that have ever been imaged. That's not how we find them, by looking at a star and seeing that there's another planet. We have to find them by inferring that they're there. Um, and because that is hard and complicated, the planets that we find have a tendency to be larger than average, much more massive than the Earth. They have a tendency to be closer to their parent star, meaning their orbits have a small semi-major axis. They have a tendency to go around rapidly. Their orbital period is small. And it's also easier to find them if they're relatively big planets like Jupiter, but their star is relatively small, that is, smaller than the sun. So therefore, we have to say that we're learning about planets, and there are now about 6,000 exoplanets that have been discovered. But the question is, are they typical of all the planets in the universe? And the answer to that we know is no, because our methods are very highly biased towards finding unusual ones that are large, massive, close to their star with short orbital periods, and their stars are of relatively low mass. The other thing is we learn about the planets using different methods. So in some cases, we can figure out the mass. In other cases, we can actually figure out what the atmosphere is composed of. But in some cases, we can't do that. So keep that in mind. Okay, so the free floaters are really strange because our idea of how a planet forms is that a planet forms at the same time the star forms. And in fact, the star forms and it will also be surrounded by a ring of dust and gas, which collides and builds up and forms planets. So we don't understand how you actually form planets when there's not a star. And we discovered these mainly because we're observing a star very carefully, and the star brightens and then fades in a very symmetric way. In other words, it gets brighter and then it fades in the same way that it got brighter. And this is due to the fact that the gravity of the planet causes the light from the star passing behind it, because they're both moving a little bit, to bend. And I talked about gravitational lensing before. When I talk about how we find planets, I'll talk about that again. But it's due to Einstein's theory of gravity that says that gravity should bend starlight if there is a little planet that happens to cross in front of the background star. The only we think that probably these planets that are planets on the loose or free-floating planets, rogue worlds, whatever they want to call them, were probably formed around a star and then due to some sort of gravitational interaction They were thrown out of the stellar system, the planetary system, and ended up on their own. But it's also they formed some other way. We don't really know, but there are a few examples that have been discovered serendipitously when people have been observing stars and discovered that they must be gravitational lensed by a very small object. So there are a few of them known. One of them is as massive as Jupiter, but appears to be embedded in a disk of dust, rock, and ice. And the other one is smaller than the Earth. So again, we don't know very much about them. We can't see them. We only infer their existence. But since they don't have a star nearby, they must be incredibly cold and dark. Not a good place to live. Okay, another example of weird planets, and I guess we get to see a little animation here. I hope it shows up, is a planet which is a hot Jupiter. In this case, the planet um, has about the same size and mass as Jupiter. It has an orbital period of only about 2.2 days. And the animation doesn't show you very much. I guess it's better to see the picture that I clipped from it. This one is, again, it's a hot Jupiter. The atmosphere contains a lot of silicate. The atmosphere reaches a temperature of about 2,400 degrees Fahrenheit. At that temperature, silicate forms grains of glass. So imagine that this atmosphere of the star is full of of vaporized glass, which forms a kind of molten rain. The planet is moving really fast because it's in this tight orbit around its star. And so if you were to try to fly into it, it would be like flying into a rainstorm composed of glass with wind speeds up to 5,400 miles per hour. Again, a really weird place, completely unlike anything we know about in the solar system. Here's another one. This is called tick. These things have very long numbers. In this case, the orbit is extremely eccentric. So I'm going to stop it when it gets to out there. I hope you can see the orbit. We'll get rid of that. You can see the orbit here for the planet is superimposed on the solar system, just to give you a feeling of the scale. It brings the star the planet close to close 10 times closer to the star than Mercury is for a very brief period of time. And then the planet moves out in its orbit so that it ends up about where the Earth is. So this planet would feel a huge difference in the amount of sunlight it was receiving when it was at periastron compared to when it's at apastron. The star that it orbits is a little bit bigger, hotter, and more massive than the sun. And so the difference in the temperature between being here or being out here is huge. And so the seasons would be caused by the elongation of the orbit, and the planet would be submerged in a huge radiation field and get really hot here, and then it would cool off as you went further out. Probably not a good place to develop life. Okay, here's another one, which is called um, the egg star, the egg planet. It is in a death spiral, we think. Again, it's got an elongated orbit. Sometimes it comes so close to the planet that it is wobbling a little bit as it moves around. It receives intense radiation from the host star. It's spinning rapidly enough that the planet itself is oblong like an egg. It's interesting in that, like the moon, its rotational period is tidally locked to its orbital period so that one side is always facing the star. The star is a little smaller and cooler than the sun, and the orbital period, this planet goes around the star every 1.1 day. And the daytime side gets so hot, hot enough to vaporize iron and titanium. It gets hot enough that its star is not much hotter than the daylight side of the planet itself. And so we believe that this planet, as it it's so close to its star, it's eventually going to be evaporated, or at least the outer layers are going to be evaporated. So again, here, as it goes around, the outer layers of it are probably being stripped off the star. Again, not a great place to want to develop life. But these are the planets that we see. So here's another one called the Kryptonian planet, which we think is the exposed core of a gas giant whose hydrogen and helium have been blasted away. So this planet might have been like the previous one, but we're observing it at a later stage in its evolution. In this case, this one is more massive than Neptune, about 40 times the mass of the Earth, but it's only slightly bigger than the Earth, which means that it's relatively dense. And the idea is that the hydrogen and helium, which was in the extended planet when it was more like Neptune, has been evaporated off. In this case, it's on a pretty circular orbit today, now, but it might have been on a more elongated one in the past. It's very close to its star, and the orbital period is about 18 hours. Yeah, Hank.
So, Martha, does Jupiter have a core like this planet?
Yeah, probably Jupiter does, but of course we don't see that. Um, and it's the core is at the center of the object. What we see, of course, is the atmosphere. As the case with the sun, which has a very dense core. It's not rocky, but it's very dense. And then the outer part is lower density. Or Venus, which has a very thick atmosphere and a rocky part underneath. Because I don't typically think of Venus as looking rocky, but that's because we can't see through the atmosphere.
And does
Mercury,
that core, I'm sorry, does that core generate heat?
yes, there's some heat, but that's not really what's causing the planet to be hot. It's the sun. Stars are hotter, but the core does have some heat, and it can generate some heat due to radioactivity, in fact.
Thank you.
So again, what we think this one is probably a later stage in the evolution of one like the one we just saw. Another example of what we call a hot Neptune is a planet that's the size of Jupiter. And if you remember the picture, Jupiter and Saturn were quite a bit bigger than Neptune and Uranus. This one is the same size as Jupiter, but only has 5% of Jupiter's mass, which is, again, means that it's been inflated, we think, so that it's fluffy. It orbits a star like the sun, but it orbits with a period that's only about 7 days because it's incredibly close to the star. the outer layers are being heated up, and that causes the atmosphere to expand. We also think that it gets so close that some of the material from the star from the planet falls onto the star, causing the explosions on the star or flares, which then blast the planet with extra radiation. Again, not a nice place for the development of life. Similarly, there's another one which we've discovered, which is called the Marshmallow Planet, which is not a hot Neptune, it's a warm Neptune. It's almost as big as Jupiter, but it has less than 1/10 of the mass. But this one is interesting because JWST has been able to look at this planet and get a spectrum, and the atmosphere of this planet contains water vapor, sulfur dioxide, and we believe clouds of sand, meaning dust, meaning silicates, actual solid particles rather than just water. And it again has an orbital period of only 5.7 days and a surface temperature of 700 degrees, which is pretty warm, but not as warm as the hot Jupiters. Another one is a gaseous mini Neptune, which is twice as large as Earth and 8 times as massive as Earth, and it's very dense, although we're not really sure if it's rocky. It orbits in the habitable zone of a small, cool red dwarf star, so that it's way inside the orbit of Mercury and has an orbital period of about 33 days. And again, what's interesting and what JWST allows us to do, not for all the planets we found, but for this one, is it has water vapor, methane, carbon dioxide, and possibly, although this is debated, dimethyl sulfide, which is a potential biosignature. And this has only been discovered very recently. Again, we need more information. This is what we call a Hycean planet, a planet which actually appears to have abundant water underneath a hydrogen-rich atmosphere. It appears to have a superheated and supercompressed ocean where water exists somewhere in the threshold between being a liquid and a gas. So, again, interesting. Okay, so let's just talk a little bit about the Earth-like planets. What's an Earth-like planet? It's a planet at the right temperature within the habitable zone and only about 1.5 times the diameter of the Earth, that's in orbit around a star that's like the sun. We have an example of one of those. It's called the Earth. So we can see if we can find other planets that are similar. And as you can see here, there are a bunch of them. They were all discovered by a telescope called Kepler. So again, about habitable zone. The habitable zone is the region within which the temperature of an average planet, the temperature can depend on the atmosphere, but the temperature of an average planet would be correct so that liquid water could exist. That depends on the temperature and the size of the parent star. And so for a hot star, you expect the habitable zone, which is the green zone here, to be further out. For a cooler star, the habitable zone will be closer in. And of course, the sun is just in the right place. So if we follow the Goldilocks principle, the habitable zone is where it's just not too hot, not too cold, just right for liquid water. So here's an example of a planetary system around a star that's called Kepler 62. In other words, it was the 62nd star found to have planets by the Kepler satellite. It has at least 5 planets, 2 of which are within the habitable zone. The star is a little smaller and cooler than the sun. So here's the solar system and Mercury, Venus, Earth, and Mars. And Venus is just on the inner part of the habitable zone. Mars is just on the outer edge of the habitable zone. Earth is right in the middle. Here's the habitable zone of the Kepler 62 star system. The star is smaller and cooler, so the habitable zone is closer into the star. And again, there are 5 planets, 3 of which lie too close into the star to be in the habitable zone, but 2 of them are in the habitable zone. They're called F and E, and I've just thrown them up here in reverse order because 62F is the one that's more like the Earth, more maybe Earth-like. It orbits further out than Mercury, sort of kind of like where Venus is. It has the length of a year is 267 Earth days. The radius is about 1.4 times the Earth. The mass is about 2.8 times the Earth. The average temperature is about minus 85 F for this planet. Because even though it's closer in, it's around a much cooler and less luminous star. It is because of its density, it's believed that it could be rocky. We don't know that it's rocky, but it's dense. The other one, E, is a mini Neptune. It is closer in, and its temperature is about 26 degrees Fahrenheit average. It's bigger, so we classify it as a mini Neptune, but it appears to have a density so that it's probably gaseous. Now, the one that people call Earth 2.0, has a radius of about 1.6 times the Earth and a mass about 5 times the Earth. It has a fairly high density, so it, again, could be rocky. It orbits at 1 astronomical unit around a sun-like star, which is old, which again means that there could be a lot of carbon there. Just 1.5 billion years older than our sun. It has a similar temperature. The star, it is almost sun-like. The orbital period of the planet is about 385 days, and the average temperature is about 17 degrees Fahrenheit, kind of like it was earlier this morning. This is very suggestive that this is an Earth-like planet in a habitable zone, but we don't yet know enough about its composition to be able to say that it could host liquid water. But this is the kind of planet that future observations with more and more sophisticated telescopes will focus on to try and find out if it has an atmosphere that could have water. Okay, so what I hope I've tried to do is tell you that the Earth is boring relative to all the other exoplanets that we know. That, of course, may be the reason that we're here, because the Earth is rocky and otherwise unremarkable. It's not being evaporated by the sun. The sun itself is a mature, stable, old star with relatively few stars nearby. So life in the solar system is pretty mundane. The solar system is stable. The planets follow largely circular orbits in the same plane. There aren't things whizzing in different directions. We do know about 6,000 exoplanets. We find a lot of them that are really weird. The most common exoplanet that we find is the hot Jupiter. But we find them because they're big and they're hot Jupiters as opposed to our Jupiter because they're very close to the star, but that makes them easier for us to find. But I think it's also interesting that we have found Earth-like planets in the habitable zone around sun-like stars that have been found. And astronomers are going to start looking for those. And probably in the 2030s or around 2040, there will be another NASA mission called the Habitable Worlds Observatory, which will be designed to look for and study Earth-like planets in the habitable zone. Um, Also, our catalog of these planets is growing rapidly, and JWST has also broken open the possibility of studying the planets, exoplanets that are discovered to teach us about the composition of atmospheres. But it's probably true that the reason we are here is because the Earth is boring. So I hope that hasn't disappointed you. Anyway, that's all I wanted to say. And anybody have any questions? And that's why we call it the Goldilocks principle. Okay, I've got Alan and then Hank.
Thank you, Martha. That was great. As it always is. You mentioned these rogue planets that were seen by microlensing, and I think in one case you said it was going through some kind of I forget exactly how you described it, some kind of matter field. Um, I was wondering about two aspects of that. One, in general, uh, do you really get repeated microlensing observations of these things? And two, uh, that matter field, is it something other than around a star? I mean, it seems like it would have to be if
Okay,
you were describing rogue planet.
you've asked the two perfect questions. Okay, so first of all, a microlens event you see once, and essentially you're looking at a star, and all you see is the star. But over a period of time, the star brightens very characteristically to a little bit, and then it fades in a completely symmetric way. I mean, oftentimes you have flares where on a very really short period the thing brightens and then fades because there's some kind of an explosion, like a supernova or a nova. In this case, you can watch over a longer period of time a very well behaved brightening and then an equally well behaved decline in the brightness. And the other thing that tells you it's a microlensing event and not something else is that if you observe the event with different filters at different wavelengths, you see exactly the same phenomenon at each wavelength. It is not color dependent. It's achromatic. Every other explosion event in the universe you would expect would show some difference in the brightening that has to do with the temperature of the explosive event. A microlensing event happens once, and it's completely symmetric and achromatic and occurs over a longer period of time. And so the way they do that is people have programs that just stare at places with a camera and watch and look at hundreds and hundreds and hundreds of stars at the same time and keep their fingers crossed that something will happen. And then they compare all the images. Um, so so that's the first how you know that it's microlensing and not something else. The other thing is weird is that one of the two that I mentioned, shows some evidence that there's not just a single object, a single planet. There's some there's some structure to the microlensing event that implies that there's a circular orbit, but that there's also some kind of a ring system or disk around it. Okay, which causes a slightly different structure in the microlensing, but again, nobody understands it. And the difference between we also find planets because planets eclipse their star. But that's a different phenomenon. That would be periodic. But microlensing is usually a one-time only event, which means they're kind of hard to study because you can't go back and look at it again with a different telescope. Okay, Hank.
Thank you again, Martha. Back to the good old Goldilocks principle, which focuses on the temperatures associated with water being available and so on. What then is it that causes us to have water on the Earth, not have water on the moon, which is in the same distance and so forth from the sun? Fundamentally,
Well, yeah, it depends on whether or not you have an atmosphere. Our atmosphere keeps some of the heat in. We also think that the moon formed in some strange way, such that its hydrogen and helium, the hydrogen in particular, got blasted off.
uh,
But again, also think about the difference between Mercury, Venus, Earth, and Mars. Venus has this incredible greenhouse gaseous atmosphere, which means that the surface of Venus is incredibly hot. So it's not as simple as your exact location tells you exactly what the temperature is going to be. The composition of the atmosphere and planets haven't always been in their orbits forever. Planets, over the course of their formation, planets often move around from outer to inner or inner to outer, depending upon where other bodies are. And so a lot of things can happen, but it is true that you're right. The moon does have water, but only at the poles.
okay.
The moon has the moon has gone through a rough existence. It's been bombarded and it has no atmosphere. So again, the Goldilocks principle has to hold. Everything has to work right, or else it's unlikely that you can have life develop because the Earth has to have been boring for a long time, including now. And
And the
that again,
moon that's lost its
and the,
atmosphere for a reason other than distance to the sun.
That's right. The moon went through some kind of collisional, probably collisional event that got it to get attached to the Earth or knocked it out from the Earth. We're not 100% sure.
Thank you.
Um, but the fact that life exists on Earth is probably because the Earth has not had an exciting life and lives in the right place at the right time. And so that's why you will, when people talk about they've discovered this exoplanet or that exoplanet, they're normally telling you that they've found something that's really weird. But we have to keep in mind that the really weird people, really weird sculptures are the ones that people recognize and talk about. The things that are boring, we have a tendency to ignore. And today, because of how we discover exoplanets, we're going to find a lot of the weird ones first, but they're not necessarily the average one. So that's what I just wanted to say. I hope it was interesting. And I'm not sure what I'm going to talk about in March. I haven't figured that out. But I think in April, I promised David round that I will talk about dark energy and dark matter and what's going to happen to the universe. So again, if people have topics they want me to talk about, I make it all up as I go along.
Thank you so much.
Okay, well, again, February 28th, you can look for the planetary and alignment, if I find that. If you look later this week, if it's clear, you look after sunset, you can find Venus, Mercury, and Saturn, and Jupiter will be bright up high. And also, if you're up at 6 o'clock in the morning on March 3rd, look for the total lunar eclipse very close to the horizon in the west, just as before sunrise.
Thank you,
And
Mark.
with that, I apologize that we're going to take away an hour of your sleep on March 8th, but you'll get it back in the fall.
Thank you.
Okay,
Thank you.
bye-bye, everybody.
Thank you, Martha.
Bye. Thank you.